Hi, I'm Teacher Thomas. Welcome to math class. This video is regarding a Pure Maths 3, 9709 Pure Maths 3 concept from the topic for vectors. Foot of perpendicular is sort of a particular or specific application of a more general concept. We'll start with the foot and then we'll generalize to understand how this concept relates more broadly. Note that when we're working with the foot of a perpendicular has an angle of 90 degrees. And the scalar product when the angle is 90 degrees equals 0. That's a particular scenario in which we'll apply the concept we're about to look at. In other cases, you'll be given an angle, not told perpendicular, which means the angle is 90. You'll be given an angle, and then there'll be some tweak to the algorithm that we'll be working with. So let's look at this algorithm as I've typed it and then talk about what the scenario is on the right side written. First, we'll be given a point and we're given a line. Sometimes we need to find the line using vector techniques. Step one is get from point to line, and that will be some kind of expression in terms of a variable. Usually that variable is lambda. From there, in the specific case of a foot calculation, we know that the scalar product is 0. So what are we getting the scalar product of? It's the component we find in step 1, the scalar product of that, and the line direction. Those will be perpendicular. If we look at a diagram of what this would look like, we'll be working in 3-dimensional, but visualize just the 2-dimensional component. If we have any particular line and a point out somewhere, we can go to that line at an infinite number of spots. It's the one in the middle that I've drawn. This is a sketch, but the idea there is that we have a 90-degree relationship. So if we were to, that's taking a 3D and putting it onto a 2D surface, but there's some other angle, another dimension involved we can't see. If you visualize a pencil horizontally and another pencil vertically, the pencil vertically sitting right on top of the pencil horizontal. You could sort of shift that in a 2-dimension plane and change your angle smaller or larger than 90. If you shift it in the 3-dimension plane, so say you're going to shift back and forth towards you, you don't really see any change in the angle because that's in the 3rd dimension. But if you're shifting side to side in the 2 dimensions, you can see a change in the angle. The 3rd dimension isn't important. We're only focusing on the second, we're focusing on 2 dimensions. So if we know we're looking for a foot, then the relationship in that 2-dimensional scenario is 90 degrees. It is possible that from the point to the line, we can shift. We won't necessarily always be at 90 degrees. What we're going to do is a calculation, given that we're at 90 degrees, what is it that we're going to do with that information? We'll see as we work through the algorithm. With that, in step 3, we're going to put the lambda expression into the line equation. The lambda value, rather. In step 2, we find the lambda value. Then in step 3, we put that lambda value into the line. That results in a direction vector from the point to the foot. Typically, the question is going to be a position vector. So we want from the origin to the foot. And the way we get there is step 4. The point plus the result of step 3. And my comment about format. Usually the format is going to be a vector format. So you'll have either component form or column form, but you'll have a vector. It might be point format. What are the coordinates of the point? And then you would use that format. So if we had the example, let's say we found, to be clear on the requirements, if we found the point of the foot is 4, 1, 6. And the requirements were the point of the foot, then we're done. If the requirements are the position vector of the foot, that we would write as 4i plus j plus 6k. So again here, there's no question or scenario this actually applies to. I've just pulled this out of the air as if this had been the solution to a problem. Those are the requirements you're given. You want to think about which format is appropriate. So let's work through an example, and then I'll give you a textbook question relating to foot and some past paper questions. One relates to foot and one relates to a more generalized application of this concept. Speaking of that, before we go to the example, looking over on the right side of this board, what I have written in purple. Step 2, I'm changing. If we're given a particular angle, then that's not based on the perpendicular relationship, which means that the scalar product is 0. So if we're given a particular angle, then what we're doing is finding whatever lambda we find will fit based on whatever the scalar product that we set up ends up being. So it will be something like you could be given a point and a scalar product of 0, if that's perpendicular, and then you need to find the value of lambda. Or you could be given a point and told that the angle is a particular value. Then you don't know what the scalar product is, but you can calculate the scalar product, put all of that information together, and in whether it's the scalar product is 0 because it's perpendicular, or the scalar product is something else because there's a particular angle given, you're not solving for a specific value. You're going to solve to an expression in lambda in either case. So then staying on the right, looking down to step 4, there's another change. Step 4 of the foot of the perpendicular, you're restricted to perpendicular relationship. And that 2 dimensions, as I've drawn over on the left, you have the perpendicular relationship. What it could perhaps look like in, there we go. What it could perhaps look like in a more general scenario is we've got a line and then a point, and we might be told that we're looking for an angle of, let's say, 75 degrees. And we're going to do some calculations. There will be an expression in t, and then we might need to find perhaps a relationship between these 2 components of a line that we're going to split. So that's quite general. We'll see in the last example, whichever one that is, the third or the fourth, that I'll ask you to work through where this more general concept comes into play. So let's do an example starting with foot. And I've made this up. Let's say you're given the point of 1, 2, 3, given the line equation of -152 plus lambda -1, -2, -3. You might, in your requirements, need to do some work to get to that line equation, but here it's given. So find the direction vector from point to foot and position vector of the foot. Notice requirement B isn't the point of the foot, it's the position vector of the foot. So we want to give a vector answer, not a point answer. Let's go back and follow the algorithm. So 1, point to line in terms of lambda. So for 1, point to line. What that means is line minus point. When you're doing vector AB, you want B minus A. Here we're going from point to the line minus point. So the line component is going to be, and we're using in this step, let's go back to the general slide, and I'm going to post on this board parametric form. is fundamental in using this algorithm. So I want my x component first, a line minus point. There are two parts for the line, -1 plus -1 times lambda. Okay, the -1 from any point I have plus -1 times lambda. Minus the point component of 1. And then for this is going to relate to x, and then relating to y. Similarly, 5 plus -2 lambda, I'll simply write that as -2 lambda, minus and then the point of 2. Then for the z, 2 minus 3 lambda, minus the point component, minus 3. And let's note that the 1, 2, and 3 are coming from the point. 1, marking these in orange, 2, and 3. I realized after I worked through this problem that in picking -1, -2, -3 here, it's possible that you'd look over here and see -1, -2, -3 and make the wrong connection. So notice that as I've written up at the top, minus point, those components of 1, 2, 3, those came from the point components. Okay, we can simplify each of these. We'll end up with -2 minus lambda and 3 minus 2 lambda and -1 minus 3 lambda. Continuing step 2, the scalar product of the result of 1 and the L direction, the line direction. So for step 2, we're going to have the line direction over on the left side and the components from step 1 up above on the right side, scalar product of those. So -2 minus lambda is my first component from step 1. And scalar product, the direction of the line, first component is -1. And then the second component, product of second component of each will be 3 minus 2 lambda times -2. And then third component, -1 minus 3 lambda times -3, which will equal 0. Okay, we can simplify the right side of the scalar product equation because a component is multiplied by cosine theta. The angle is 90 degrees because it's perpendicular. Cosine 90 is 0. Whatever we multiply by 0 results in 0. So simplifying now, we want to solve for lambda. So we have -2 times -1, that's 2, minus lambda times -1, plus lambda, then plus 3 times -2, minus 6, -2 lambda times -2, plus 4 lambda, then -1 times -3, plus 3, -3 lambda times -3, plus 9 lambda equals 0. We can simplify to the 3 lambda terms, 1, 4, 9, 14 lambda equals, and then moving the constant terms over, -2 from +2, +6 from -6, -3 from +3. And if we divide by 14, then we end up with lambda equals -2 plus 6 minus 3 is 1 over 14. Continuing, step 3, lambda into the line. That will be from point to foot. So let's show here visually. Let me take a look at my colors. Okay, I'll use gray here. In step 3, we're going from point to foot, going to the diagram over on the left. Okay, what I'm Now tracing over in gray, that's from point to foot. Foot is a particular point on the line, and we're starting with some given point. This is what's happening in step 3. Let's begin with an update to the algorithm. In step 3, lambda into line is improved as lambda into the result of 1. So in step 1, we found point to line in terms of lambda. We used that in step 2. We're going to use that again in step 3. So let's see what our result of 1 is. On the right side in pink, -2 minus lambda. So I'll leave that lambda out for a moment. And then 3 minus 2 lambda. And I'll leave that, I'll put brackets blank for a moment. And then 1 minus -3 lambda. -1 minus 3 lambda. We have a particular lambda value that we're looking for. That lambda value. But before we have the lambda value, let's go back to the diagram for a moment. So here what we're doing on the lower left with the relationship between the pink line and the gray that's going from one point to the foot is based on a 90-degree relationship. Based on that 90-degree relationship, we have a particular lambda we're about to input. Until we input that lambda, what we know is we have this gray line that's going to we have a point-to-point connection. A particular point to some point on the line. There are an infinite number of points on that line. So now we have, in step 2, come up with the lambda to give us the particular value that we're looking for. So we're going to take the expressions we found in step 1, put in the result lambda, the particular lambda from step 2 based on the 90-degree relationship. And what will then go away is these other options. And we only have that perpendicular from the point to the line in a perpendicular relationship. That's what we're finding in 3. So what lambda did we get? 1/14. And we end up with -29/14. 3 minus 1/7, 20/7, -1 minus 3/14, -14/14 minus 3/14, -17/14. This is point to foot, which I think in the scenario I set up, direction vector point to foot. That would be requirement A. So for A, the direction vector will be -29/14I plus 20/7J minus 17/14K. And that is, in English, that's from the point we were given, 1, 2, 3, 2, foot. Step 4, let's go back. Step 4 is let's see what our requirement, it's origin to foot. The formatting will be based on the particular requirement, but we definitely need information about origin to foot. Here will be position vector of foot. So we're not looking for the coordinates, we're looking for the actual position vector. Per our algorithm, that is going to be point plus the result of 3. The point is 1, 2, 3. So we will have 1 plus 2 plus 3 plus. Those components coming from the given point. The results of 3 are -29/14, 20/7, and -17/14. The results are 14/15/14, and then 14 over 7, 34 over 7, and then 42 over 14 minus 17 over 14. It's going to be something positive over 14. 42 minus 17, 25. And given the requirement of the direction vector, we want to answer B in a vector format, not a point format. The point of the foot is negative 15 over 14, 34 over 7, 25 over 14 for the x, y, z values. We're writing in vector form as negative 15 over 14i plus 34 over 7j plus 25 over 14k. Let's look at a visual analysis of how we get from 3 to 4 so that graphically, visually, you have some guidance in what's happening. Whoa. Okay. I'm going to have a point, P, and what we found in A was to get from that point to some line such that from P to the point on the line, we have a perpendicular relationship. Here's what we were doing in part 3. What we're doing in part 4 is we're finding from the origin the position vector from O to the point, not P, but the foot. And the algorithm said add something plus something. What the algorithm is telling us to do is over in for what I'm doing per the algorithm is point plus 3. So what's happening in the diagram is the point is a vector. We can make the point a vector, OP. And so what we're doing in step 4 is point plus 3 is OP plus, and what we found in 3 was P e to the point on the line. And so that is P to whatever we want to call that point. And then according to vector algebra, that is going to give us O to the point, okay, the point on the line to be specific, dealing with 2 points, the given point and then a point on the line. So there we can see graphically how the algorithm ties to a vector algebra concept. OP plus P to point equals O to point. And that final vector, O to point on the line, is in red. So let's see 3 examples now. 2 relate to foot and 1 generalizes the concept. Here from the Cambridge University Press text. This was in the vectors chapter. Question 7 gives a line equation and gives a point. In A, the point is 5, negative 3, 2. Okay, that point is over on the right. Oh, actually, that's not the point. This is some other requirements you have in here. The point is given in B. B is show that the point A that relates to whatever you're doing in requirement A is the foot of the perpendicular from. So using the algorithm, the point that we're starting with is point B. And the line equation we're given Okay, so the line equation we're given is L1. Notice that in B, we're looking for a relationship between the point and L2. So there are some additional requirements to be clear in using the algorithm that I worked through in our example. The point and the line that we're working with, point given, line isn't given. There's some other information you need to figure out that line. Because the concept is foot of the perpendicular, when you work with the angle, scalar product / angle component, you're going to think about scalar product equals 0 because the perpendicular relationship means the angle is 90, cosine of 90 is 0, thus the scalar product is 0. This is March 20, paper 32, question 8. And here you can take a screenshot or you can pause the video, you can pull this paper up or download if you don't have it. Notice in C, foot. So again, some additional requirements that you need to do. But in C, the idea is working with a particular point, working with a particular line, finding the foot. You can go through that algorithm that we used. And the third example, June 21, question 32. In this case, notice that in the requirement A, we have use a scalar product to calculate angle AOB. So the angle isn't 90 degrees. The scalar product isn't 0. This isn't a... It's possible that you could end up with a scalar product of 0. And if you did end up with that, then you know you have a perpendicular relationship. But this is not specifically foot, therefore not specifically 90 degrees. So the scalar product may not be, probably won't be 0. So how will the concept apply that we're working with, the algorithm apply? Let's see what we have following A. The midpoint of AB is M. The point P on the line through O and M is such that PA to OA is root 7 to 1. Find the possible position vectors of P. What will probably happen in B, the plural possible vectors, you'll probably have some kind of quadratic and then have two solutions with which you can find these two vectors. Let's do a rough, very rough, because it's two-dimensional diagram of a three-dimensional scenario and look for what's going on here. The midpoint of AB is M. We're given A and B. I'm just going to randomly draw them in. Okay, not making any attempt. You might make some attempt for some more to scale, but again, because it's three-dimensional, I know that's challenging. I'm just going to put points A and B down. And you have A and B information in the givens. From A to B, we can connect and make a midpoint of M. Okay, and you can do some calculation to find the particular coordinates of M. The point P on the line through O and M, so let's put an origin somewhere and then draw a line through O and M. And that line doesn't stop. Okay, it can go for as long as we want in two directions for that matter. So the point P on that line is such that PA to OA is root 7 to 1. Find the possible position vectors of P. So what's likely here is that we'll have some P that's between O and M and some P that's beyond O and M. And the relationship of PA to OA, PA or PA to OA, the OA component is a measure of 1, and the PA components are measure root 7. Now, if those two pink lines are the same length, they are mathematically. They don't look They certainly aren't the same length the way I've drawn them. But again, there's a scalability limitation because I'm trying to do a three-dimensional concept on a two-dimensional board. But that's the idea behind this problem. So it's not that there is a 90-degree angle. There's some other angle, but with all of that information, using the rough visual that I've presented here, you can work through the procedure to find what are those two possible, and notice that your requirements are position vectors. So once you find P1 and P2, then you want to make sure that you write them as vectors from point O. And if we go back to the intro board, we'll see on the right-hand side the changes in the algorithm. Step 2, we have a given angle in that last example that we looked at. And then in step 4, there's some required value based on the relationship of 1 to root 7, or in that particular case, 2 required values. That concludes the lesson on what I'll describe as vectors parametric equation applications.